मगर इस देश रहना चाहिए, इस देश का लोकतंत्र में रहना चाहिए।
You can do one Mumbai, you may lose Balochistan.
2, 1, 0. S139 mortar.
This man is a horrible man. He must be shunned.
For them to count. Our job is to hit the target, not to count the body bags.
Welcome back to the show. And again, once audience also, we are glad to have you here.
Okay, so the topic today I think is quite interesting. No, we will touch on quantum technology and try and relate with our spirituality and try and mix science and spirituality, and then string theory. What do you say, Parth?
Absolutely. Much of our ancient knowledge also has some underpinnings of science. Humans have been people who are doing critical thinking for a long time. So, we can definitely review some of that.
Okay. So should we start with quantum technology, which is quite buzzing in the social world?
Sure, sir. I think we have heard about quantum technology or quantum communications or quantum computing, but I think maybe we can hear from you, like since you have been the expert in this area for very long, maybe you can tell us something about this, so the audience and even myself, I can understand something more.
So first, nobody is an expert in quantum, let me tell you, and I have very little basic understanding of quantum. And even the experts in quantum say if you find quantum complicated, it means you're in the same realm as we are. Everybody finds quantum very complex and very difficult to
That's
understand.
Richard Feynman's quote, basically.
Yes. So see, I have had my stint with quantum in 2019 and 20, where in our army military college we created a quantum technology lab, and that is a time where I had interaction with the experts, industry experts, and Indian scientists for quantum technology, and there were various symposiums which I have attended. So what actually, if you say quantum, what generally people know is quantum computing, but quantum information technology is the bigger umbrella, wherein there are four different verticals. The first vertical, which commonly we know, is quantum computing. When we say we get quantum computers and they will crack the code so easily, and WhatsApp can be cracked very fast, and all these things which are buzzing the social media. Second vertical is quantum communication, wherein you might have heard in 19 and 2020 that China has done trials of quantum communication over satellite and fiber, and it is going ahead in quantum in the race. This is one fear where quantum communication will come in a big way, and quantum key distribution is what is being addressed there. The third vertical is quantum sensing, wherein you will have telescopes and MRIs machines coming with quantum technology, which will have portable MRI machines or portable telescopes, which will see much better resolution than what classical telescopes and MRI machines. I'm just giving a few examples. And the fourth vertical is quantum spectrography, where assessing the layout of land, maybe, or various places can be done. So we'll concentrate today mainly on, say, quantum computers and quantum computing and quantum communication. So I'm sure, Path, you're a computer engineer, and you tell me what you know about your quantum computing, and then we'll start from there.
Sir, in the most simplest of words, I can describe quantum communication or quantum computing like a paradigm of doing something on the principles of quantum mechanics.
Yes.
That is what it is. And there will be different applications of the quantum mechanics which exist, which will be applicable for communications, which may be applicable for computing, and many other things like that.
Yes. So you're quite right. See, quantum mechanics or quantum physics is the physics of subatomic particles. So I'll just tell you a background. See, Newton was our premier in classical physics, wherein bigger particles physics was in one way defined by Newton's laws. Okay, and how bigger particles move. When I say bigger particles, means particles which are bigger than atoms. Okay, so their movement, their physics, their gravity, movement in space. Even Einstein, if I say, is again some portion is with his classical physics, in the sense that he defined how these particles. When I say E is equal to mc square, when energy mass conversion, all these. But they always classified either things into matter or energy, and Einstein gave a relation between energy conversion of energy to matter, and Einstein always said that if you go with speed of light, there will be no particle behavior; it will be all wave. So either you exist in particle or you exist in wave. Like photons, they are waves, but they exhibit particle nature. So this is what legacy physics is. But once they went inside the atom, the atomic nature, like the electrons primarily, photons also is again in one way subatomic. So there you find that it behaves. There is a duality. It either behaves as, it can behave as particle also and wave also, which was not agreed by Einstein. So there is one Heisenberg uncertainty principle, which says, like in Bohr's model, we state that there is a center atom and the electrons move around in circular orbits. Heisenberg uncertainty principle.
Maybe you can explain what is orbit and things like that, because
So
maybe
if
for
there
the
is a,
regular audience.
yes, so if I take Earth as one of the atom, center of the atom, a proton and neutron, which generally is taught in class 8, 9 physics, the electrons move in certain orbits. First orbit will be the closest. So next orbit, like there'll be 2 electrons, then 8 electrons. There are formula for how the atom structure will be, and Bohr's atomic model is based on that. There it defines that the proton and neutron will be at the center, like Earth, and like Moon, the electrons are moving around in certain locations only, in certain circle orbits only, like satellites we see, right? So some 2 electrons will be closest, then 8 will be the next ring. So it will be like rings. And he said the electrons are moving around the atom in rings. But Heisenberg uncertainty principle said that this ring is not actually the location of the electron. The probability of finding the electron there is maximum. To find the electron, it is uncertain. We do not know the position of the electron till the time we physically hold the electron or physically take a snapshot of the electron. So electron exists if we take a snapshot or we hold it in some way. Otherwise, it is a wave. So this was quite confusing, right? So Heisenberg uncertainty principle defined that electron is actually a wave, and it behaves a particle when it is caught for some, say, passing current or something like that. So in a very layman term, this is one thing which was quite different from what classical physics is. Secondly, another matters of this is called principle of superposition. You don't know exact position till the time you hold it or you take a snapshot. Okay, the first theory which I mentioned was a theory of superposition. Now, second is a theory of entanglement. What in a very simple term is that I can generate 2 electrons with the same energy level and with the same spin, either clockwise or anti-clockwise. So they behave like twins. In one way, their energies, their states are entangled. They are connected to each other. Now, in a very simple way, like हमारे पुराने फिल्म में आता था राम और श्याम, twins. So they are like twins. Okay, राम को अगर पेन आएगा तो श्याम को फील होगा. It's very very identical, and it is so सुनने में लगता है it is ये क्या मजाक कर रहा है, but it is in the actuality. If you can produce 2 electrons or photons with the same energy, same state, and you take one electron to moon and keep the second one here, and you measure on earth का electron या photon को, उसका say temperature, sensitivity or pressure, anything you measure, actually it gives the data of the electron on the moon. Now Einstein was not agreeing to this. Einstein said, yeah, this is what do you mean? The information is traveling faster than speed of sound. मतलब उधर मून है, इधर ही मैं चेक कर लिया, उसको इन्फॉर्मेशन आने में भी तो स्पीड ऑफ लाइट में भी कुछ टाइम लगेगा. How can you say this is possible? But it was possible. So Einstein was also proved wrong.
This is the one in which we are talking about the entanglement. This is the image that they are capturing.
Image of entanglement. If you see, there are two dots. Say one red in color, if you see the color, and one is green. So these are entangled subatomic particles. This can be electrons or photons. I'm not aware which he's showing. But what I mean to say is, somehow their souls are joined.
It's a photon.
So somehow their souls are joined. So in one way, if you do any experiment with one, you get the behavior of the other. Again, this is very very spooky, right? This is Einstein used to say this is spooky. This is like not normal. Okay. And further, after Heisenberg's answer, I just mentioned superposition. When I say superposition, it means you don't know where that uh, particle, subatomic particle is existing. It can be in any state. It can be in any location. First of all, it is uncertain, and secondly, it can be located anywhere. So if I hold, suddenly if I hold, it's like a revolving ball very fast. I hold it, I find it here. This is my observation. The time I'm observing, I locate its location. I pinpoint its location. Otherwise, I don't know where its location. So when I say superposition, it can be in any state, right? So just imagine an electron can be at so many states. Now coming to computing, yeah, you have some
So,
query,
so,
please ask.
so we can fairly say that like an electron is that handyman that you are trying to call, and when you catch him, then he's there. Otherwise, you
Yes,
don't know what is his
yes.
position and
Well,
location.
I really don't know. So that is what these three basic principles of quantum define, and it is quite spooky, right? It is quite out of the classical sense ki you एक uncertainty है, एक superposition, I don't know where the position is. Secondly, they can be entangled. So these subatomic particles which are smaller than the size of atom actually behave very different from the classical physics, and this is called as quantum physics. In a very plain layman term, I've tried to explain to our audience. Though the science is very complicated, the algorithms are very different. Now coming to the application. Now let's apply this. So for say quantum computing. Now strength of computing, or the order of computing, defined by number of registers you've got. Each register can store a bit, either 1 or 0. Okay, in binary system. So if I've got 8-bit register, I know 2 to the power 8 is the values I can store. But what if in each register, instead of ones and zeros, there can be infinite, a very high number of states. So the electron there can either be 1 or 0 in a binary system, but in quantum computers, it can take multiple states. So if 2 to the power 8, whatever the value comes to, instead of 2 to the power 8, it is 2 to the power 8,000. Then you can imagine the computation power of a small quantum computer. So quantum computers can have very large computing capability. So what a normal classical computer the same size may do processing in few hours, a quantum computer may do it in seconds. So bigger problems like CERN labs and all the people who have black hole and space, NLP problems, very complex problems which are taken by classical computers years to compute. Okay, there are in IIT I decided actually सुनने में अजीब लगता है, but there are some codes which you run which can take days, right? Those can be done in minutes. So, but it is for specific high level complexity programs. It is not for our everyday coding and everyday gate resolution programs. So this is one vertical which I have discussed is quantum computing, and already I think Parth can give info on quantum computing links and websites which are already there of IBM and other applications.
In fact, even India, we ourselves have launched the quantum mission, and for reference, I will just present it here for the audience so that it is going to make more sense. Now here.
Yeah, National Quantum Mission.
So, the Department of Science and Technology by government, they have, secured so many of the, thematic hubs or T hubs, where every hub, let's say, is doing a lot of innovation. Like, for example, in Bengaluru, they are doing something in quantum computing. In IIT Madras, they are doing something for quantum communication. Then in IIT Bombay or IIT Mumbai, they are doing something about quantum sensing and meteorology, which means I think measurement and weights, all these things. Then at IIT Delhi, there is something to do with the quantum materials and devices required to achieve all the remaining other things. And if you see, there are so many institutions which are supported under the National Quantum, mission. And if I just try to zoom it up, you can see that there is so many of these, and many of them are very, very renowned institutions throughout India, which are doing a lot of work in this area in research and PhD, and many of the students are also working for this under the different professors in the labs.
Okay, and just for the info, even for the defense forces, we have an MCT, a Military College of Telecom Engineering, where I was one of the professors there. we had built a quantum information technology lab. So that is where I was heading next. That the first vertical is quantum computing, which we have discussed. And what I was trying, Parth, to tell us that we've got online links and websites like IBM and other big companies which offer simulated quantum computing experience. You can you can give this task to those simulators and quantum computers, and it will give the task to you a very basic feel of how quantum computers, not in the commercial way but in a way to understand how the quantum gates are different from classical gates, and quantum computing is much different. Yeah, I think Parth has some experience in this. Parth, you can give your personal experience.
Yes, yes. So I tried running some programs on the IBM, quantum computers. If you know how to program in Python, then they have something called as Qiskit, which
Use.
is this particular program or this library. So you're able to program, some kind of a quantum computer using just Python programming language. If you know the concepts, and you're able to make it work. Lot of these are present, like code examples, tutorials, and things like that. So IBM does have some real world computers which are available to the public. As far as I'm aware, this is the only instance where we have a IBM, or at least a cloud computing availability. The other one which I know about is from AWS. That's called
AWS.
AWS. They have AWS Braket, which is the quantum computer cloud service. But I personally haven't used it myself, but I have heard that that exists as a resource for people
I
to use.
think this is a 64-bit quantum computer experience which they give you, IBM.
So that is variable. There are different kinds of quantum computers over there. Depending on capability, the price is different.
Define.
There is no standard answer to that question. It depends on the
But
application that you're
as per
putting.
the research, uh, I think 128-bit is what quantum computers, the research and other things are going on. But yes, commercially, quantum computers are still not being used, and they are generally there for research and further development. So that is where we end our discussion on quantum computing. Now, next vertical, we'll go on quantum communication. Now, quantum, if again I come to the electrons and photons, one thing I do, I generate entangled photons or electrons. If I talk of photons, right, you showed the image of photon, and I put it on a optical fiber from, say, Delhi, and I let that optical fiber run till Kanyakumari, and I take that electron, right? It is an entangled electron, so its nature is very defined. Okay, what if somebody eavesdrops and tries to get that, and that photon is carrying some important information? I can map my bits onto photons. The data can be mapped on optical photons, right? That is how normal optical fibers, we basically map our ones and zero bits into the intensity of the photon, and that is how the information is carried in the optical fibers. So what if somebody wants to eavesdrop and take that information? So he has to physically catch the entangled electron. He may get the information if he knows the coding, and if I assume that all the complexities are removed and he's able to retrieve. But once he retrieves it, he cannot, but he has to pump in the electron again and send it to my destined user so that I am not aware, right? As a cyber attack, if in eavesdropping you listen and you again send the information back so that the user, sender and receiver, do not know that somebody is eavesdropping. The point is he cannot generate that entangled electron in any way. Whatever entangled electron he generates, it is very unique. So he cannot copy the same electron. And if that he pushes a duplicate photon or electron, at the other end, I can understand because you not matched my original entangled. Because एक का copy तो मेरे पास है. It is something like I have a 100 rupee note जैसे पुरानी movies में आते थे ना, I tear it. अब वो जो उसका दूसरा टुकड़ा लेके आएगा जुड़ेगा तभी मुझे पता ही original है. So the point is you cannot eavesdrop. So see, encryption point of view, this is the highest encryption possible. Hence, in communication, primarily for quantum key distribution, it is used. So what I can do is I can encrypt my information in quantum in terms of entangled photons and electrons. Photons primarily because it travels larger distances, and it will be totally safe. It cannot be eavesdrop. It cannot be copied. It cannot be replicated. Hence, for important, say, defense and high level or PMO level or government level, high level information which is top secret can be encrypted in quantum entangled photons and sent across the network without being anybody able to. And if somebody tries to eavesdrop, I'll come to know. So I will already destroy that code and send a new code. You'll be surprised to know that in military we have a lot high level of encryption in devices, and those codes, they come from army headquarters and come from high levels, and they are very I cannot name the organizations who approve it, but those keys are physically taken to all the distant remote locations of the country, physically fed into encryption devices, okay,
Yeah.
through
Just
remoting
like
devices.
in World War II era, they used to have the keys for Enigma machine. In the similar way,
So
maybe
World War
or
II
more
is quite, no,
advanced
these
way.
are very modern machines, so there's not but the
I
concept is
mean to
same.
say,
So
I
encryption,
mean to say
there are
the
two
concept.
types. Yeah.
I mean to say
So
the concept
encryption,
remains the same.
no, concept has drastically changed, but yes, on the whole, there are two types of encryption. One is symmetric encryption, one is asymmetric encryption. So there are, we'll not get into the encryption and cyber technologies, but what I'm trying to say, these keys, instead of physically carrying it for secrecy so that nobody gets hold of it, I can send it through quantum key distribution networks where quantum technology is used. So this is one primary application, and China has been very advanced in these, and it has already tested and demonstrated in its newspapers that I've tested quantum key distribution over so and so fiber length of 200 kilometers, or through satellite I'm able to transfer these coded keys to the other end. Even the banking systems can take use of it by employing such, if it's a very high top secret information or codes which need to be transmitted from one location to the other of the country. You can use quantum encryption or quantum key distribution. You encrypt it through quantum electrons and photons entangled, and then distribute it through the network. So this is the highest level of encryption which is possible. Even AES 256 or 512 may not be able to do it, because physically you cannot replicate the same electron or photon. This is the second vertical which we wanted to discuss. Yeah, Parth, you want to say something?
I think primarily in simple terms, if I understand this right, and I'm saying this for the audience, it means that if somebody tries to listen onto any conversation which is encrypted by quantum communication technology, then that whatever message is there will become corrupt or useless. That is a fair
Yes,
assessment.
and the user and the sender will know that his message has been intercepted. So the
Yes.
interception will be aware, and then it loses its cause. Okay. To end the podcast, what I'll say is these. Before I end, I should also touch the other two verticals. Is quantum sensing, when I said that MRIs and telescopes will be much small and much capable of seeing vast distances. A handheld MRI, you don't need a big MRI machine, because if you go by the same logic, if I can send one photon into a deep space, I can, the entangle its twin is with me. I can just use its information to find information which is far vast, light years away. Same way for a human body, if I can send one photon into your body, I and the second entangled photon is with me, I can take the information of the photon which is entered your body and see the image. So this will actually change the way we have been scanning and seeing things. So what we'll see commercially is your sensing, and quantum computers will come in hand in big way, and quantum communication. So these three verticals we have touched, and I think this is enough for today and for the audience to just have an understanding of what is quantum technology bringing to the common man, and in the future which it comes. And lastly, one more point: quantum communication will not be used, or encryption will not be used for our basic handset normal discussions. It will only be used because you cannot encrypt the entire payload of IP packets. You may have specific IP packets. The quantum billions of IP packets cannot be encoded. It takes time, and it will be much overhead. So the processing time is also involved. Hence, for only specific applications for high, as I mentioned, the top secret and high secret messages of the government and the defense forces will be encrypted. It will not be for common usage. It will be for specific usage. All quantum computers, quantum communication, quantum sensing. So that is where I finish for today.
Yes, sir. And I think this sums it up for me and the audience. Very well put. And I think we'll come back once again on that. And before we sign
Yes.
off, sir, can you please tell the audience about your book? We flashed the.
What we'll do is मैं अभी सोच रहा था 25 हो गया तो क्वांटम में इसको क्लोज करते हैं, इसके बाद एक और रिकॉर्ड करते हैं स्ट्रिंग में, देन विल से क्वांटम और स्ट्रिंग का हमने क्या स्ट्रिंग में बुक को करते हैं,
नहीं, दोनों
स्ट्रिंग
में
के साथ
डालते हैं ना, फाइन, दोनों में डालते हैं, इट्स ओके.
अच्छा चलो ठीक है. So, as Parth has said, I have written a book, Astral Matrix, which is just behind me. And though I have not used concepts of quantum, but yes, we have to know that our Sanatan text and these science, they actually merge somewhere. And whatever concepts, the way legacy science is, legacy physics, classical physics is actually changing. And if you see quantum, many things are related, which the common logic science is not able to say. And somewhere there are Sanatan texts and Sanatan concepts come in handy. I think we'll also discuss string theory if you are interested in the next podcast, and we'll try and link string theory and concepts of quantum with our Sanatan concepts which we already know. And you'll be happy to read this book. It is a very short book, Astral Matrix, and I've asked certain basic questions of life in this. And this is the link in the Amazon. It's a very 60 pages fast read book on science and spirituality relationships. So I think it will be a good read for people who are interested in science and spirituality.
And please feel free to scan the QR code and go on Amazon and buy it. Amazon is offering good delivery.
Try and see. Yeah, it will help you see spirituality, the Sanatan Vedic concepts in a scientific way. Yeah.
Okay, sir. So thank you, sir. Let's connect on the next podcast once again.
Yeah, we'll try and explore new concepts like quantum.
Yeah.
Thank you.